All right, everybody. Hello. There are fewer of you today, which means that your classmates are either in the rain or are too stressed about the exam to come here, which is probably, sorry about the stress. Periodically, I run into people, that's a chemistry dad joke. I run into people out in the community, sometimes with their significant others. They've taken my class. I always apologize to the significant other for the stress I've caused in their relationship. Okay, so I'm doing something a little unusual today. I've tried to hook my phone up to my computer so that I can show you close-up models, and that's probably a better way of trying to talk about conformations in organic molecules and trying to draw them. We'll draw a little bit later today, but what you have here, if you can see it, is what we're going to call ethane, just a 2-carbon molecule, only I've arranged so that one of the hydrogens is green and the other hydrogen's blue. This is our view from the side. This is our view, and if you were looking at this and trying to draw this from the side, the green atom, let's see, here we go, that'll work. The green atom, the carbon, the other carbon, and then this hydrogen here are going to be all in the plane of the page, so those would be straight lines. This hydrogen would be on a wedge sticking out at you. The hydrogen you can't really see unless I tilt it a little bit is right here, and this would be the dash going away from you. You can't, sorry, we're struggling with the camera. All right, that'll work. Similarly, over here, this would be, the blue atom would be a dash, and then the other hydrogen would be a wedge, okay? We call this the staggered conformation of ethane because if you look at it straight down the carbon-carbon bond in this sort of Newman projection perspective, you can see that all of the carbon-hydrogen bonds in front are staggered or interdigitated with the carbon-hydrogen bonds in the back. We've talked about dihedral angle last time briefly. The dihedral angle is the angle between this carbon-hydrogen bond in blue in the front and then this carbon-hydrogen bond in green in the back. The angle between those two vectors, it's almost like you've pretended this isn't 3 dimensions. You've smashed it down to 2, and you're just measuring the angle between those two. And in this conformation, that angle's about 60 degrees, okay? Right. So what I tried to show you last time in the simulations from that gallery of molecules was that you can spin around a carbon-carbon bond, but all of the dihedral angles that you can adopt are not the same energy. By the way, while we're speaking of dihedral angles, this is an eclipsed conformation, one in which the CH bond in blue in the front is eclipsed with the CH bond in green in the back. That dihedral angle is what? 0, right? So you go 0 staggered, 0 eclipsed, 60 staggered, 120 another eclipsed, 180 another staggered. When the dihedral angle between two groups is 180 degrees, we'll say those groups are anti or opposite of each other. So now I'm getting to the point where I can't start doing math beyond 180 degrees. So another 60 degrees dihedral angle and we're eclipsed, another 60 and we're staggered, and now we're back. So we've got 3 different staggered conformations and 3 different eclipsed conformations. This is ethane. The blue and the green atoms are just hydrogens. I'm just labeling them so you can keep track of them. So all of these eclipsed and all of the staggered conformations, rather, are going to be the same energy. Okay? And each of those staggered conformations or shapes is going to be lower in energy than the eclipsed conformations. You saw that in the simulation. You would see the propeller action going, and then as it started to slow down, it would get to a point where it was almost about to go through an eclipsed conformation, and then it would back off, and then it would kind of wiggle until it equilibrated at a staggered conformation. What that tells you is that the staggered conformation is at an energy, the eclipsed conformation is at an energy maximum, that's the top of a hill, and the staggered conformation is an energy minimum, bottom of the hill. And this is an important general thing in organic chemistry, that not all conformations are equal in energy. Some are lower, others are higher, and this matters. And this can influence shapes and reactivity of organic molecules. So this is sort of the simplest example of staggered versus eclipsed, simplest example of conformations. We need to talk briefly about why the eclipsed conformation is higher in energy than a staggered conformation. The easiest way to think of this is electron, sure, sorry, go ahead.
So what's the dihedral angle? Is that only between atoms that are bonded to different carbons?
Right, that the dihedral angle is between atoms that are bonded to different carbons. If you just do, for example, the angle between these two, that's a bond angle. You could calculate a dihedral angle between here. Okay, sorry, actually, I think technically to be not just a bond angle, the vector math requires two separate vectors where they're not coming off the same point. Anyway, there's some trigonometry here if you want to know more, which you of course don't. So yes, they need to be on adjacent carbons. Yep. Others that I missed? All right, we need to talk about why the eclipse conformation is is less stable, higher in energy, an energy maximum than the staggered conformation. The simplest way to think of this is just repulsion between the electrons in the front and the electrons in the back. They're not that close to each other if you look at it side to side, but from this perspective, they're a lot closer to each other, the electrons in the green bond and the blue bond in front and the green bond in the back are a lot closer to each other in the eclipse conformation than they are in the staggered conformation. Staggered gets them about as far apart as possible. There is another explanation that's important, but perhaps not that important for you to know about now in an introductory OChem class. It has to do with something called hyperconjugation. I think I mentioned it actually in the Chapter 4 study guide. It's always really confusing, and it's not necessarily at this stage, the payoff's not worth the pain. We will come back to the concept of hyperconjugation when we get to chapter 7 and 8, when we talk about a lot about carbocations. For now, perhaps just to mention it briefly, the staggered conformation allows a filled carbon-hydrogen sigma bond like this green one in the back to overlap with an empty carbon-hydrogen sigma star, which would be opposite this CH bond in the front in this space. We'll talk more about that later. That's just a preview. Don't worry too much about it. For right now, the explanation you can use for why the eclipse conformation is less stable than the staggered conformation is just electron-electron repulsion. Some other terms you're going to encounter in your textbook. Rotation around carbon-carbon bonds is sometimes called torsion or twisting. And so this idea that electron-electron repulsion makes one conformation more stable than another is sometimes called torsional strain. That is that electron-electron repulsion makes the eclipse conformation less stable than the staggered conformation. So torsional strain is one term you will hear for this. The other is steric repulsion or steric hindrance. Steric is a word, I'm not sure where it comes from, but we use it in organic chemistry to describe electron-electron repulsion between large groups or between groups that are close to each other in space. And so you can use steric repulsion or torsional strain more or less interchangeably to describe why the eclipse conformation is less stable than the staggered conformation. Okay, I think we beat that one to death, but perhaps not. Anyone want to get in a few more strikes? Poor metaphor. Yeah, go ahead. Are all the eclipse conformations the same energy? In ethane, where all the groups are the same, yes. Now that won't always be the case. Thank you for that lovely segue, because we're going to something that's like ethane, only the green group is now a methyl group and the blue group is now a methyl group. I'm sorry I was not able to figure out how to color the two methyl groups differently, so not so great. This is called butane. It's like ethane, only the two things that were attached to the two central carbons are now methyl groups, all right? So here is the bond we're going to be talking about, rotation around this carbon-carbon bond in the middle. And we're going to see how the presence of these two non-hydrogen groups, sorry, my hand's in front of everything, the methyl group here and there influence these conformations. So as we look down that carbon-carbon bond in the middle, let's see, we good? We can see that we are in, sorry, I don't love the camera work here, but can you get the idea? Sort of? Is that okay? No, closer isn't better. All right, we're looking down the carbon-carbon bond. This is, again, the Newman projection perspective. From that perspective, you can see that we're looking at a staggered conformation because the dihedral angle between any two groups, sorry, struggling to get on center. The dihedral angle between any two groups is 60 degrees. The angle, say, between this oh, there's my hand, sorry. This is why this is not an Instagram account that's like exploding, right? I need a film crew. By the way, my son likes me to go skiing with him when he snowboards, but it's not for the companionship, it's for the film crew. It's like, Dad, can you film me? Can you get some footy for the boys while I do this trick? And so let me get this straight. Dallin, you want me to stop here in the snow and you want me to take off my gloves and freeze so I can film you doing glorious things? It's like, yes, okay. But then he flatters me afterward and tells me how good the camera work is and that I'm the best camera work guy ever. And I'm really not, but it sort of works. So, what's problematic for me though is that if I film him doing whatever tricks and he injures himself, I no longer have plausible deniability. So I'm sort of an accomplice. Okay, sorry. Anyway, this is a staggered conformation. You can tell because all the dihedral angles are 0. So, 60. So the angle between this CH bond on the front carbon and this CC bond, the carbon-carbon bond on the back carbon, is 60. The angle between this CH bond in the front and this CH bond in the back is 60, and so on. It's a staggered conformation. Now you asked, are all staggered conformations equal or are all eclipse conformations equal? Let's just see. In the one that I've shown you here, the two methyl groups that are on these two central carbons, the one in the back and the one in the front, are anti to each other, okay? We rotate 60 degrees. Let's see how we're gonna do this. And we'll go through an eclipsed conformation. Now if we look at that, the methyl group in the front is eclipsed with a hydrogen in the back. Here's the methyl in the front. Here's the CH in the back with which it is eclipsed. Sorry, struggling to give you the right angle. All right, so that's one eclipsed conformation. It's really surreal trying to watch the camera and try to move things myself. All right, get the right angle. There we go, that's better. Okay, if we rotate through another 60 angles, another 60 degrees, we'll get a staggered conformation that looks like this. Now notice this staggered conformation is way different from this one. In this one, the methyl groups are anti to each other. In this one, they are pretty close to each other. In organic chemistry, we're going to use a word for two groups that have a dihedral angle of 60 degrees with respect to each other. That word is gauche, G-A-U-C-H-E. French-ish, meaning what? Left? Yeah, I don't know why, because you could say, well, it's maybe, okay, one methyl group is to the left of the other, but then you have to switch. Okay, one is still to the left of the other, so maybe that's why, I don't know. I don't exactly know why we call it that way, but that is the terminology. So we would say those two methyl groups are gauche to each other, whereas in this staggered conformation, they are anti to each other. Got it? I'll get to the issue of the eclipse conformations in a minute, but let's talk about gauche versus anti. In the anti conformation, the methyl groups are pretty well as far apart as possible. I'll show you that from the side. And you can see they're not sort of anywhere close to touching each other. So the electron-electron repulsion between the methyl group in the back and the methyl group in the front is minimal. Now, if we adjust that dihedral angle and go to the gauche conformation, one of the gauche staggered conformations, you can just sort of see that they're pretty close to each other. Really hope I press record. Good, I did. Yay. But from the side, you can now see that they actually are much closer to each other. This distance between the two methyl groups is much lower. One thing actually to mention about model sets like this is they're really good at showing you where the bonds are and where the atoms are. They are terrible at showing you how much space things take up. So you may want to, and in just a second when we transition to the iPad, I will show you a space-filling version of what we're doing now, and you'll see clearly that the methyl group here occupies sort of space that I'm circling, and the methyl group here occupies space that I'm attempting to circle while not moving from the camera. And those are close enough to each other that there's some substantial electron-electron repulsion. So what I'm telling you is this conformation, this gauche conformation, is higher in energy than this one. Okay? Now, you should be able to see pretty clearly how if we rotate through another 60 degrees, another 120 degrees, to get to this staggered conformation, this one should be exactly the same as the other one. Right? Do you see the two methyl groups are similarly close together? In one case, they're sort of, I mean, technically, if you want to be precise, if you calculated the dihedral angles with vector math, one of them would be positive, the other would be negative. It's clockwise versus counterclockwise, not particularly important. But you can see that they are equivalent. So you've got 3 staggered conformations with butane. 2 of them involve gauche interactions between the methyl groups, and one of them is anti, and that's lower in energy. All right, let's go through the eclipsed conformations real briefly. As I said, starting from this anti-conformation, if we rotate 60 degrees, we go through a conformation where the methyls on either side are eclipsed with CH bonds, so that's one. Okay, that's worse than a staggered conformation. If we continue through, there's the gauche conformation. Now we get through an eclipsed conformation where the methyls are eclipsed. Which do you predict is higher in energy based on torsional strain? This staggered conformation, sorry, gonna get that wrong every time on the first time. This eclipsed conformation or this one? That one, right? The second, and that's because of electron-electron repulsion. And you can even see they are knocking into each other there, right? That's electron-electron repulsion. Good. If we continue to go through and rotate another 120 degrees, we go through another eclipsed conformation. This one should be identical to that one. Okay? So, gauche, anti. Yeah, I'm sorry. You were pointing at the periodic table and not even waving at me, but I'm waving back. You ever done that? Waved at somebody that wasn't waving at you? That's all kinds of fun. Okay, so those are conformations of butane and ethane. And in general, you can make the molecule more complicated, but the idea is you want to keep the largest things farthest apart from each other. Here's an interesting observation. If I'm in this gauche conformation, and I want to get to the other gauche conformation, what's my lowest energy pathway from getting from gauche 1 to gauche 2? Is it to do what I did? My heart. Ooh, you can't see, right? Is it to do what I just did where I rotate, from your perspective, counterclockwise, going through that eclipse conformation to get to that one? Why not? So I just told you this eclipse conformation is the worst one, right? Probably in order to get from here to here, instead we're going to go the long way around, rotating through the lower energy eclipse conformation to the, you should sigh in relief there as you see that anti-conformation. Okay. And then uphill again to this eclipse conformation, which is high in energy but not as bad as methyl-methyl eclipsed, and then here to the other gauche conformation. And there's good evidence that this is the case. Now, your text and in some notes that I can provide will show you some energy diagrams where on the y-axis we have energy, and on the x-axis we have dihedral angle between the two methyl groups. And I'll show you sort of how energy varies as you go around this circle. But you'll see that this is the energy maximum. Here is a local energy minimum. Here's another local maximum, but not as bad as the methyl-methyl maximum. Here is the global energy minimum, okay, the lowest. Here's another local maximum, but not as bad as the methyl-methyl eclipsed. And then here is another local minimum, not as good as the anti. Okay? So this is what we've just described is called a potential energy surface or landscape. You have hills, you have valleys. The valleys are the minima, the staggered conformations. The hills are the maxima, the eclipse conformations. The eclipse conformations are transition states. They are places you have to get through to get from one conformation to the other, but a molecule will never sit like this for long. Yeah?
So if electrons don't like to be near each other, why do gauche interactions even form? Why don't they just stay far away?
Why do gauche interactions form? Great question. So the issue is, if this is the lower energy conformation, why does this one ever happen? The answer to that has to do with two things. First, how different are they really in energy? I don't have this number memorized, so I got to look it up in my notes. It turns out that the gauche conformation is about 3 kilocalories per mole higher in energy than the anti-conformation. Okay? That number may mean nothing to you. First of all, in terms of energy, you've been dealing perhaps in general chemistry with joules. I'm sorry, but organic chemists by tradition prefer kilocalories. That's okay if you like joules, kilojoules instead of kilocalories. The magic number is 4.184 joules per calorie, I think. Maybe it's the other way. I don't care. Organic chemists by tradition like kilocalories per mole, in part because we have over the years developed an intuitive feeling for what kilocalories per mole mean. At room temperature, an energy difference of 1.4 kilocalories per mole equals a factor of 10 in equilibrium constant. Okay? So based on that, if this is 3 kilocalories per mole, I could tell you that at equilibrium, the population or the amount of molecules in the gauche conformation is going to be substantially smaller than the amount in the anti-conformation. And you can tell by exactly what amount, all right? The second issue, in addition to that energy difference, is how much kinetic energy a molecule has. We've described a potential energy landscape where minima are lower in energy than maxima, but your ability to traverse that potential energy landscape depends on your kinetic energy, in the same way that your ability to ride a bike up a hill depends on your kinetic energy, right? Temperature is simply kinetic energy of molecules. It took me like 40 years to realize that, so I now impart that knowledge to you freely. Temperature of molecules is just their average kinetic energy. And so the question is, at a given temperature, does a molecule have enough kinetic energy, say, to overcome the barrier between anti to eclipsed to gauche? And the answer is yes. So you can rotate pretty freely around this bond. At equilibrium, you would expect there to be more anti than gauche. But you would, and as to how fast you interchange one to the other, that's an issue of do you have enough kinetic energy to overcome the barrier. I will say for the ethane molecule, the barrier to go from, and what I was describing there was energy differences between minima, right? The energy difference between the anti-minimum conformation and the gauche local minimum conformation. It turns out, I don't have the numbers here, but I think the methyl-methyl eclipsed interaction is maybe 9 to 10 kilocalories per mole, higher in energy than the anti-conformation, and that's probably too high of a barrier to be traversed at room temperature. Back to the ethane molecule, the barrier between between two different staggered conformations, here's one, here's an eclipsed, here's another staggered conformation. That's uphill. The eclipsed conformation is about 3 kilocalories per mole higher than the staggered conformation. And at room temperature, you have plenty of kinetic energy to easily go through that barrier. Okay, so that's a ton of stuff. Yeah, go ahead.
So is there ever going to be a situation where eclipsed is better than staggered?
Is there ever going to be a situation where eclipsed is better than staggered? I can't think of one. Unless, you didn't want to hear that, you tie the molecule up such that it can't do anything else. And this has to do with making rings. That is, we can take the molecules that we have and we can make cycloalkanes, all right? So maybe I've got some notes that I will post about ethane and butane eclipsed and staggered conformations. You'll see it on paper. It will mirror what you see in your textbook. I felt like it was better in class to actually look at the model. Now that means you're probably not scrambling down to draw stuff, because I haven't been drawing stuff either, and that's okay. You'll have those notes, and I would encourage you to go through looking at those notes, maybe perhaps as you watch the replay, to get a sense for what we're talking about. But I want to spend a minute talking about cycloalkanes. And we'll do this with a model set. So this actually is going to answer your question about is there ever an eclipse conformation that's okay. Look at butane and imagine, and notice that as we've drawn it here, those two methyl groups are eclipsed. That's an energy maximum. Let's force it to be that way. So to do that, we'll simply remove a carbon-hydrogen bond, remove a hydrogen, and we'll make a ring. Okay, da-da-da, cyclobutane. Now, let's look at the challenges associated with cyclobutane. I will tell you, by the way, cyclobutanes are found all over nature. You can make them. They're not impossible compounds. They're not particularly unstable. But I want you to look at the dihedral angles in cyclobutane and compare them to what we know about eclipsed versus staggered conformations. So as I look down a carbon-carbon bond, let's say this one, what do you notice about the CH bonds in the front and in the back? They're eclipsed, right? That would be, you would predict that would be unfavorable, right? That would involve some torsional strain, okay? Also, if we look down a different set of bonds or compare where the carbons are, let's look down the bond between this carbon in the front and this one in the back. Those two other CH2 groups are eclipsed with each other. They have to be. We've paid for that a little bit with that other bond, but that's another example of torsional strain. There's something else to be aware of as well in cyclobutane, and that is, let's look at the molecule, and as I've drawn it, or as I've made the model, all the atoms, all the 4 carbon atoms are in the same plane. What is the bond angle for this carbon? 90 degrees, has to be in a square, right? A flat square has to be 90 degrees. What would it prefer to be for an sp3 hybridized carbon? 109.5, but we don't need to know that number to that many significant figures, all right? Ooh, that's the one time in this class you're gonna hear that word, so there it goes, significant figures. So that introduces something called angle strain, which is for an sp3 hybridized carbon, it would prefer to be 109. It's constrained, there's the embedded word, constrained to be 90, so it's less stable than it could otherwise be. If we sort of zoom in and you look at my model set, you can see that those bonds are straining a little bit. Those are just sort of flat plastic cylinders. They're supposed to be straight lines. You can see them bowing a little bit to accommodate the square, right? And in fact, actually, you could say we could build a molecule that has a smaller ring, but it suffers from similar issues. This is cyclopropane, and I really sort of have to crank on it to get it to form. I will say that cyclopropanes are very common in nature. They're important molecules in organic chemistry. They're not crazy unstable, they're not unheard of, but if you look at cyclopropane, again, you've got even worse angle strain because 3 points define a plane, and a triangle, the internal angles have to be 60. Now there's some formula for what the internal angle of a polygon, a regular polygon is. I don't care what it is. I looked it up and then promptly forgot it. But I do know for the triangle it's 60 degrees. But you can see the angle strain because these carbons actually are built with the places where you put other atoms at exactly 109 degrees apart. So in order to accommodate this geometry, you really do have to bend those bonds. So you've got angle strain in cyclopropane that is worse than for cyclobutane. For cyclopropane, you have these same issues of eclipsed. As we look down the bond between the carbon in the front and the one in the back, you can see that all of the CH bonds have to be eclipsed. There's no solution, all right? Now, that's okay, as I said, cyclopropane is not that unstable, but cyclobutane has options because, as I said, with cyclopropane, 3 points define a plane. For cyclobutane, though, you got 4, and so you can relieve some of this angle strain and some of this torsional strain by taking a couple of these atoms and moving them out of the plane. All right, so we can look at it from the side. Maybe this is the best way. I'm gonna take, all right, center, good. I'm gonna take this one and tilt it sort of upward. And I'll do the same here and then tilt the other ones downward. That's called puckering. I don't know why. I think you have to imagine that this is lips and then they're like something. But you see, if we pucker the ring, if we go from being flat to having the two atoms opposite each other coming up out of the plane, look at what that does for our bond angles and our torsional strain. We can now look down a carbon-carbon bond. We'll look down this one in the front, sorry, trying to get center, and this one in the back. It's not an eclipse conformation anymore. It's not perfectly staggered. The dihedral angles are not 60 degrees if you look between this bond in the front and this one in the back. But it's better than eclipsed, right? And you could do the same all the way around. If we were to focus on looking down this carbon-carbon bond and looking at the relationship between those two groups, the carbon in the front and the carbon in the back. Again, it's not perfectly staggered, but it certainly isn't eclipsed. So by puckering, the ring can relax some of the torsional strain. It can also relax the angle strain. This is a little bit more difficult to see, but those angles are not constrained to be 90 degrees anymore. They're somewhat larger than that, a little bit closer to 109. So what this is intended to show you is that aside from cyclopropane, rings for saturated hydrocarbons made of sp3 carbons are not generally flat. They pucker or distort from planarity to relieve angle strain and to relieve torsional strain. All right, so we could talk about this for the 5-membered ring, but that's probably a topic for, angle strain is less for a 5-membered ring, and torsional strain is also less for a 5-membered ring. But probably for an introductory OChem class, it's probably best just to now talk about the 6-membered ring, which is cyclohexane. So, and we're going to transition to the iPad in about 5 minutes once we're done talking about this with the model set, because you are going to need to learn how to draw this puckered shape of a 6-membered ring. Yeah?
What was the difference between torsional and angle strain?
Right. Torsional strain has to do with electron-electron repulsion because of the dihedral angles. That's eclipsed versus gauche versus anti. Angle strain has to do with the fact with differences between the preferred bond angle for an sp3 carbon and what it would have to be in a flat polygon, right? So with cyclopropane, which I just broke, so sorry. Okay. So for cyclopropane, the bond angles, cyclopropane has to be flat because 3 points define a plane. The bond angles here have to be 60 degrees, but they'd prefer to be 109. That difference means that the atoms are closer together than they would prefer to be, and that's angle strain. Yeah. All right. So you are going to have to learn to draw what I'm going to show you is the puckered conformation of a 6-membered ring. It's going to be called a chair for reasons that require you to tilt your head to the side and relax your eyes and imagine an Adirondack chair or something like that. But we'll get to that in a little bit. So here is cyclohexane, 6-membered ring. I've tried to make it so that all the atoms are in the same plane. And if that's true, the internal bond angle would have to be 120 degrees. Now that's not smaller, as was the case for the cyclopropane and cyclobutane. That's actually stretched out larger than you want to be for an sp3 hybridized carbon, right? sp3 wants to be 109. In a hexagon, you'd need to be 120. This is another kind of angle strain. It's the same thing, but it means stretching too far, right? Stretching too close versus stretching too far. Similarly, if we look at the planar flat conformation of cyclohexane and look down a particular carbon-carbon bond, you would see that all of the, why can't we get it? Struggling to get the right perspective. Okay, I don't know. Fine, I think that's going to have to be good enough. You can see if this is the carbon in the front and this is in the back, all the CH bonds are eclipsed with each other and all the CC bonds are eclipsed with each other. Now, because it's larger, cyclohexane has more options for puckering than, say, cyclobutane. And it turns out that if I take every other atom, so maybe color would help us here. So I've got some orange hydrogens here. If I take, sorry, and then I want a different color, which I don't have, orange. Maybe I'll also just take these ones and make them blue, if that's okay. All right, so if I take the orange hydrogens and I pull them upward, like this, so that they're sort of pointing straight up, and then I take the non-orange hydrogens that are pointing downward on the other three carbons, I can get a conformation that looks like this. And this is the chair conformation. And before we worry too much about it, we're going to go through this in a ton of detail. But before we worry too much about it, I just want you to notice the features of this conformation and how relaxed the six-membered ring should feel. Like relative to the cyclopropane and cyclobutane, the six-membered ring is really chill. All right? Did I use that appropriately? Maybe not. Meaning the carbon in the front here and the carbon in the back, that is a fully staggered conformation. Those dihedral angles are all 60 degrees. The angle between the orange proton in the front and then this CH bond in the back, 60 degrees. Also, notice the carbons, okay? We're still focused on this carbon in the front and this in the back, but the CH2 here and the CH2 there are gauche to each other, staggered, not eclipsed. That's as good as you can get in a ring, okay? And so we could go looking down each and every carbon bond in the molecule. You can see staggered conformation there, staggered conformation there, staggered conformation there, and so on. So cyclohexane actually has no torsional strain. Its dihedral angles are exactly the same as you would want in a not cyclic hydrocarbon. Another interesting feature is if you look at the bond angles, the puckering has, and this is hard to appreciate other than by maybe looking at it from the side, looking at the angle between these two carbons, noticing that those plastic bonds are not bent or strained in any way. It turns out 109-degree bond angles, perfect for this chair conformation. All of the bond angles internally there are in the puckered cyclohexane chair conformation are 109.5. So cyclohexane also doesn't have any angle strain. So it's this nice little solution to the problems of organic molecules conformations in the sense that you can form a ring, but if it's got 6 atoms in it, you can have perfect bond angles and you can have perfect dihedral angles such that there's no angle strain and there's no torsional strain. All right? A couple of things to talk about with this chair conformation. And for that, I think I'm going to need some other colors as well. All right, so sitting down here, maybe I'll lift it up here. The reason it's called a chair conformation is, let's see, if you, as I said, relax your eyes and look at it from the side, these two bonds here and here are the arms of the chair. This is the head of the chair, or where you put your back, and then this is the foot of the chair. Don't try to get it too far. We just call it a chair and move on with our lives. Now, notice that in the chair conformation, the environments of the CH bonds are different, okay? Some of them are pointing straight up relative to the ring. These are the orange ones, okay? We call those axial in the sense that we're making a metaphor that there's sort of a sphere that's wearing the cyclohexane ring as a belt. And the North Pole would be here and the South Pole would be here. These orange protons are axial. They're pointing upward to along the axis of the sphere. The yellow ones here are also axial. The orange ones we'll call axial up, and the yellow ones we'll call axial down. There are also protons that are around the periphery of the ring, or if we keep along the idea of a sphere wearing this cyclohexane belt, those would be along the equator of the sphere, or we call these equatorial protons. So the blue one here is equatorial. It's pointing to the southern hemisphere of the sphere of our globe. So this would be an equatorial down proton. The white one is equatorial but up. It's angled upward towards the North Pole, right? So again, you got to imagine a sphere wearing this belt, a North Pole and a South Pole and an equator. Protons that are pointing towards the North Pole are up protons. Protons that are pointing towards the South Pole are down protons. Protons that point directly along the axis of the sphere are axial. Protons that point out sort of towards the periphery are equatorial. But you got axial up here in orange, axial down here in yellow, equatorial up here in white, and equatorial down here in blue. Axial versus equatorial. All right, that's important because there is actually another chair conformation that this molecule can adopt. We can, if you play with a model set enough, you can tell that you can rotate around carbon-carbon bonds a little bit in this ring, and if you do this, you can interchange one chair for the other. So I'm going to actually grab a hold of each of these axial protons, and I'm going to turn them downward like this. As I do that, did you notice the equatorial up proton in white popped upward and became axial, right? So I can do that here, and I can do the same thing over here. When I do that, I get a fully lovely chair conformation, but things have changed. The orange protons, which used to be axial up, are now in an equatorial up position. They stayed up. Flipping the chair doesn't change up to down. Up stays up and down stays down. But flipping the chair does allow you to convert axial to equatorial. So the orange proton, which used to be axial up, is now equatorial up. The white proton, which used to be equatorial up, is now axial up. Now look what happened to the blue proton. This used to be equatorial down, now it's axial down. And the orange, try again, third time's a charm. Its yellow proton used to be axial down, and now it's equatorial down. When going from one chair to the other, up stays up and down stays down, but axial goes equatorial and equatorial goes axial. We'll learn how to draw that, and I'll show you that next time. But I want you to know that in a cyclohexane ring, you have two chairs. And this now lets us, there are periodically nerd code words you can use to identify other nerds. So here's one of them, and maybe it's the first one from this class. It's the question, what is the opposite of a chair? And the answer is, of course, the other chair. There's the one chair, there's the other chair. Nonsensical, but if you use that at parties, you may identify other people who have taken this class, and then you can commiserate. So with that, good luck on your exam. Have a good weekend. I will see you Monday.